Okay, so good evening, everyone. Um, well, I don't know if you have noticed that the web page of Dr. Blasingame is down. We are we, we are aware of that, so we're working on it. So we hopefully uh, it will be working in the next couple of days. So just just so you know. Okay, so hope everyone has pizza. And again, no candies today. Sorry. So we're going to cover two topics tonight. The first one, they are going to be related to differential equations. The first one, the first topic that we are going to cover is the solution of some of cases for ordinary differential equations. And the second part of the lecture is going to be for second order differential equations. So the first order differential equations, well, they imply that they only have one independent variable. So, well, I'm better prepared tonight, so I'm not going to be struggling with a pen tonight, I promise. So first, let's classify the ordinary differential equations. As I told you, the ordinary differential equations has the property that they only depend on one independent variable, which is x in this case. So you have a function y, which is only dependent on the independent variable x. So this is we are going to focus only in linear differential equations. So to fulfill these requirements of linearity, these are the three properties that must fulfill. So as you can see here, all the derivatives are raised to the power of 1, which is the first rule. The second rule is that all the coefficients can be variable coefficients, but they have to be only function of x. And the third one is that no y or y derivative products are allowed. So here, let's explain a little bit this generalization. So on this side we have the part of the equation with the derivatives, and on this side this is the non-homogeneous part. So if this r of x is equal to 0, then it is classified as a homogeneous differential equation. Otherwise, it is classified as non-homogeneous differential equation. The solution for both cases is pretty similar. We're going to discuss it later in the lecture. So just as a preamble. Okay. So in here, the note shows some examples for the differential equations of first order differential equations. So this one is, I think, the most basic one with variable coefficients, first order. Here is a second order linear differential equation. Again, the derivatives are raised to the power of 1. Here, this is a first order nonlinear differential equation. It is nonlinear because of this exponent. It is raised to the power of 1/2. And this is the product of the y and y derivative, which doesn't fulfill the requirement of the third of the rules we defined. So most of the differential equations that we're going to be using in this course are second order linear, but if you can find some models in the petroleum literature that are non-linear, but they do some transformations related with exponential functions that they linearize these problems, such as you can solve it in a traditional linear way. So I'm going to skip until this slide where there is a summary of the most common differential equations in engineering and, well, more specifically in petroleum engineering. So most of these cases shows that they are these are given differential equations, and most of the times you solve these equations only by inspection. What I mean is, if you develop a model or you're dealing with a model with this shape, well, the solution is given by this form. And where all these functions are special functions already defined and by integrals or by summations, or depends from function to function. Most of these are already programmed either in MATLAB, Mathematica, or even in Excel. So for example, here, these are the Legendre polynomials. And this U over here, it means the order of the Legendre polynomial. I just want to verify that. Yes. Okay. This one over here are the Bessel functions of the first kind, the second kind. These are the modified Bessel functions of first and second kind, and this one is I think it is the most important for this course. You're going to find out later, or maybe you have, if you have already started with your homeworks. You'll realize that this is the most common. I mean, the basic one. So we are going to deal tonight with two methods of solution for ordinary, for first order or ordinary differential equations. First, I would like to start with separation of variables and then with the integrating factor. It is in the reverse order than the notes, but everything's going to be covered. So first, for the separation of variables, I think that is the most simple case. So separation of variables. Okay, here it is. Separation of variables. So it basically says that if you have a differential equation such as you have a function of y multiplied by the derivative, which is equal to some function of x, and this is solved only by separating variables. It is to solve on this side for the functions of y, and on this side for the function of x, like in this step. After that, well, it is only integrated on both sides of the equation, and the differential equation is solved. Sometimes this gets complicated because y it cannot be represented in an explicit way, and the equation gets ends up in an implicit way. I'll show you a case. So the first example for this method is given by this equation. So basically, sorry. In here, the problem cannot be solved. Why? Because you cannot separate the y, the variable y on this side, and the differential effects on the other side. So it is not possible to apply the separation of variables in this case. For this example, the example number 2, it is only a matter of solve for the differential of y on this side and multiply everything by the differential of x. So in such a case, after doing the separation of variables and integrating, you end up with this expression. So as you can see, it's pretty simple. It's basically solve for both sides and integrate. Here, this is a case that I was mentioning you. So let's say that you have a function, the derivative of y with respect of x is given by the quotient of two trigonometric functions. So here you can separate easily the two functions and you can integrate. However, it is not possible to solve for y. So you have solved the differential equation, but it is not possible to have a single value for y that fulfills both sides of the equation. So this is what I mean, that sometimes it gets implicitly solved. So I wanted to show you an example more related to petroleum industry. So if you remember, well, the compressibility of a fluid is defined by this equation, right? So BO is a way to express the volume of the oil, right? I don't want to go into details because, well, it's not the objective of this class, but for the sake of tonight, just consider this as a type of a certain way to express volume. So here, this is the definition of the compressibility, and for an undersaturated oil. Okay, the undersaturated oil, it means that it is a single phase, so it is only liquid. Okay, and this is subjected to the condition of when the pressure is equal to the bubble pressure, this volume is going to be equal to some reference volume. In this case, is the volume at the bubble at bubble point, right? So, well, separating variables, we get this expression, right? So after integrating on both sides of this equation, we get the natural logarithm of the factor volume, which is equal to the compressibility multiplied by the pressure plus some constant. Or if we express it in terms of the exponential function, we get this expression, okay? To obtain the value of this constant of integration, we have to apply the condition, right? The condition defined by equation 2. So when you evaluate this equation in PV, it will end up with BOB, right? So that's how you obtain the value for C, and then you get the model for the factor volume of oil. This is what you will find in any book of properties of petroleum fluids. Okay, So that's what I wanted to show you here. Now, the second method I wanted to talk about here is the method of integrating factors. So here in the notes, it is very well explained, and the mathematically elegant way to demonstrate how this is how this method is derived, but I would like to use some alternative notes that I prepared. So the integrating factor here, you have a ordinary differential equation in this shape, right? And like we have talked since the beginning of the class. So here we are going to assume that this function p of x is equal to the derivative of some function v with respect of x. So if we substitute this, if we substitute equation 10 in 9, we have this. So this is pretty similar to the product of the rule, of the derivative of the rule. So if you remember, it is given like in this shape, right? So something would be missing here. So to do so, we are going to multiply all the equation by the b function, right? So since we have done this already, we can express this in the shape of the rule of the derivative of a product, right? However, this implies that the derivative of v is going to be equal to v times the derivative of v of x. Or given the definition of px, we're going to have this equation, right? So here we only have to separate variables, the method that we took earlier, and we end up with this v, right? V, the natural logarithm of v is going to be equal to the integral of p of x, right? Or expressed in terms of the exponential integral, this is our v function. So if we substitute the function v of x in the equation of the equation 14, that it is the representation using the product rule, well, we get this. So integrating on both sides, we end up with this equation. So I don't want to use a pen. So basically, to apply this method, we only have to integrate this term and substitute in the formula here, and that's it. Following this, well, you may need to integrate by parts in order to get the general solution. So you can, this is better if you go to the internet, you see probably a nicer version of this. Right? So this is basically the solution. Okay? Okay, what else do I have here? Okay. So sometimes it is not possible to get an analytical solution. So according to Dr. Blasingham's rules, rule number 0 is cheat. And well, one way of cheating is taking approximations, right? So the approximations for this case, or the methods to approximate this, is given by the Picard's method. So the Picard's method is basically to construct a polynomial based on the successive integration and addition of terms. So in this case, in this example that we already show, which is this one, oh no, here in the notes. Well, in the notes there is another example to apply the integrating method, the integrating factor method. So it ended up with this exact solution. But okay. So the Picard's method, here you define the derivative as a function of f of x and y. So then you have, instead of, well, you have to integrate from some reference x to an actual x, right? So doing so, the reference x is no other but the boundary condition or the initial condition or some restriction that you may have. So doing so, you get the first approximation of this method. The second approximation of this method is doing a similar way, a similar procedure. Again, the integration of the function but in this case you're going to use y1, okay, which is given by this. So as you can see, as in the repetitive process of integrating, you end up with a polynomial expression, right? So here is for a third approximation, fourth approximation, and it goes on. So comparing the exact solution of this differential equation, you get this expression, okay? So it is interesting here to see that if you express the exponential function in terms of the Taylor series, you end up with basically the same approximations. But that is only until a certain point or a certain approximation. So here, the last that appears in the notes is until x power 8, right? So you get the Taylor series approximation, and this series only differ for the 8 and higher terms. Okay. So, well, personally, I haven't found this method applied in the literature, in the petroleum literature, but I don't know. Maybe it's going to be useful for you and your research. And well, this is only one example of getting an approximate solution to solve ordinary differential equations in a, let's say, semi-analytical manner. Okay, I think that's it for the first order ordinary differential equations. So let's start with the second order differential equations. So the second order differential equations have this shape. It is second order, well, because it has a second derivative. The highest order is a second derivative, like here. But again, the constants can be variable of a single independent variable. In this case is x. And it is also restricted to the function Rx. Again, if Rx is equal to 0, this collapses to an homogeneous differential equation. So the first case, and I think it is the only case that we're going to talk about tonight, is the case when the coefficients, in this case A0, A1, and A2 are coefficients, are constants. So when these coefficients are constants, well, we can assume that the solution to this differential equation is given by an exponential integral. Pardon, sorry, by an exponential function. So if you assume that y is equal to the exponential of mx, certain mx, you have the derivative of this function is going to be m multiplied by the function, and the second derivative is going to be m squared times the exponential function. So a requisite for this to be a solution is that both sides of the equation must be equal, right? So if you substitute all these three terms in this differential equation, Rx must be equal to the other side of the equation, right? So here we're going to assume that it is a homogeneous equation. That is, R of x is going to be 0. So doing so, we can reduce this expression to a second degree polynomial, right? Which to get the roots of this polynomial, well, we use the quadratic formula, right? So if you remember your algebra lectures in high school, you remember that we have three cases when if there is a solution for this if there is a solution, we have three cases, sorry. Either the roots are the same, or the roots are different, or the roots are complex numbers, right? So for the first case, if the roots of this characteristic equation are equal and real, are real and are different one from each other, the general solution for this equation is going to be by this equation, right? This is called the general solution. So if the second case is that if the roots are complex roots, one part is real and the other part is imaginary, the general solution for this differential equation is going to be given in terms of the cosines and sines. And the third case is when the roots of the characteristic equation are equal. So in such case, we're gonna have this expression, which is a term multiplied by the exponential function, and the second term multiplied by the exponential function and multiplied by x. Okay, so this is assuming that the differential equation is homogeneous. Okay, for the particular, well, before going on, I was going to show you something. There is an alternative way to express this. Well, I didn't have it here, so I'll take a risk. For the first case, there is an alternative to express the general solution for this case. You can find it like the linear combination. This is going to be C1. I'm going to call it star because it's not the same as in this equation, of sine, hyperbolic sine of mx plus C2 star hyperbolic cosine of mx. You can also find that, but it is exactly the same solution. Okay. So I'm getting better with this touch screen. Okay. So we have talked about the case when the cases when the differential equation is homogeneous, but what happens when we have a non-homogeneous differential equation? So in such a case, the general solution is going to be split in two parts. The first part is going to be covered by the homogeneous part when the Rx is equal to 0, but we have to add another part that covers when this Rx is not 0, right? So here there are two methods to do so: the undetermined coefficients and the variable parameters method. So here we're going to show only the undetermined coefficients. So I think I want to recall this expression, this Rx. So if this Rx, well, I'll start again. The particular solution, which is the one that considers whenever the ordinary differential equation is not homogeneous, will depend on the shape of the Rx. That is, if Rx turns out to be a polynomial, well, you have to assume that the particular solution is going to be given by a polynomial up to of degree m, which is the term that you're going to have in the differential equation. Or if Rx is given by a trigonometric function such as sine or cosine, where the solution, the particular solution, has to be given by the sum of sines and cosines, and for the exponential function, you have to assume that the particular solution has this shape. So I think this is going to be clearer in the upcoming examples. So here, if you assume that the Rx, the function Rx is given by this polynomial, this equation of a straight line, then this first element is going to be subjected by a it has to be given, you have to assume that the particular solution has a polynomial with this shape, right? Because this equation fits into this shape, right? Here is m equal to 1, right? 2x, 1. So here, the particular solution, you assume that the particular solution is given by this expression. So if you assume such a thing, you can verify that this is a solution if you substitute this equation and its derivatives in the ordinary differential equation, right? And both sides must be equal all the time. So if you fulfill such requirement, well, it is a solution indeed. So here, another example of a non-homogeneous solution. So you have this part, which is the homogeneous part, and this, which is the non-homogeneous part, right? So if you get the characteristic function, the characteristic equation is this one, right? You assume that the solution has an exponential shape. Then you get the characteristic equation, you find the roots, and the solution for the homogeneous part is given by this expression. It was the second case, right, with the roots of the roots being complex numbers, right? So we have this solution for the homogeneous part, and for the second part, which is the non-homogeneous part, we have this function Rx, right? So we have to consider one term here, a family of x squared, x, and 1. We have to assume a polynomial for this one. We have to assume a function for the exponential of x, and we have to assume the sum of two functions of for this part, right? Sine and cosine, which is this one. So this has to be the shape of the particular solution, right? So you define this solution, you get the derivatives, and then you substitute this into the original differential equation, right? Doing so, you end up on one side with all these parameters, all these equations. Then you have to collect and then to by analogy to find the values of A, B, C, D, E, and F, right? So once you substitute and expand the equations on the left side, and you collect the terms, like in here, then you compare for the terms that have x power of 2. You compare here, for example, ax for ax power of 2 is equal to this term, right? So that's basically what you do. You compare one side to the other, such as you determine these coefficients. And you end up, after doing a lot of algebra, you end up concluding that the particular solution for this case is given by this expression, right? Then you have to sum this particular solution to the solution for the homogeneous part, and you get the complete or general solution for the differential equation. So yeah, here the second example has two boundary conditions, right? Boundary conditions are no other thing than restrictions to get the constant and to derive a particular solution from the general solution. So for this case, this is the differential equations that we are to solve. So the first step is to assume or to solve the homogeneous part. We do that by assuming that Rx is 0. Therefore, we get the characteristic equation and obtain the roots of this polynomial, which is 1 and 2. It is the first case, right? M are the values of M are different and real. Therefore, the homogeneous solution, the general solution for the homogeneous part, is given by this equation. And to obtain the complete solution, considering the non-homogeneous part, we have this term. Therefore, we assume that the solution for such part is given by ax plus b, right? Here the Huygens polynomial is 1, therefore, well, this is the polynomial we have to assume. So again, we have this solution, take the first and the second derivative and substitute this equation, and this equation in the general differential equation. Doing so, we end up with this expression, right? This is 0, this is minus 3 times A plus 2 times AX plus B, right? Separating terms, we here it is conclude that A is equal to 1/2 and B is equal to 3/4. So the solution for the non-homogeneous part is given by 1/2 x plus 3/4. And then we have the complete general solution, which is this one. So now, given that we have boundary conditions, we apply them in order to obtain the values from C1 and C2. The first one is the first one that appears in the notes is this one, right? So we're going to evaluate the derivative of y of the general solution in 0, and we're going to set the solution to 0 in order to find Ci and C2 through a system of equations. So here we take the derivative of the general solution. We still have the exponential functions, and we get rid of this term, right? So here, one equation is defined given equating this to 0, which is this part, and a second equation is going to be given by evaluating the complete solution in 0 and equating it to 1. So doing that, we have this expression, right? So we have two equations and two unknowns. Solving, we find that C2 is equal to minus 3/4 and C1 is equal to 1. Then the complete particular solution is given by this one. So here is not general. This is particular. Okay. So here are some numerical methods to obtain the solutions for differential equations. Here some codes in Fortran, I guess. So yeah, I don't think we're going to cover this tonight. So that's all I have for tonight's lecture. Thank you for coming. And if you have, I don't know if you have questions or whatever. No? Okay. So thanks for coming.